So today we have a nice in-house speaker, and he will talk about it's Jonathan Taylor from University of Göttingen. We'll talk about essential groupoids, C-star algebras of non-Hausdorff groupoids. And he said that if the writing gets too small, please just say something and we'll throw something at him. All right, please take it away.
Thank you very much, Karen. And thank you to the organizers for inviting me here to give a talk in person. It's quite fun. We've all had a very long historical event to live through, so it's nice to kind of do things in person again. So I want to start off by quickly, well, firstly getting a bit of a poll of the room and maybe of the online group as well. Who here knows what a groupoid is and who would like me to just define them very quickly? Those are two different. Who would like me to define them?
I think some people won't know what they are.
Okay, yeah, I'll do a kind of a brief thing. So what is a groupoid? Ethically, or the kind of like, the vibe is that they're kind of groups with a partial multiplication or a partially defined multiplication, or maybe you can think of these as kind of like the middle point between just purely spatial objects and purely algebraic objects. So definition, a groupoid consists of three things. The first is you have a set or a space, so which I call G. Some people use like a math cal G, some people use the fanciest Gs they can find. I'm using groupoids too often to write fancy Gs. So this is a set or maybe a topological space. Gosh, math rec would ruin me. You have a map called the inverse, very suggestively called the inverse, which is a bijection from the set, like the set to itself, and it's self-inverse. And lastly, you have a product which is only partially defined. So we say it goes from G brackets to this space of composable pairs, which is a subset of the product of G with itself into G. And this is called the multiplication or the composition. Then, okay, I'm going to be. There are a couple of conditions. A groupoid, or well, you want some conditions on it because you don't want to just have any set with any bijection with any partially defined thing. So first condition is saying that if gamma and eta and zeta are composable pairs, then I should be able to compose them all together. And I should have that gamma and eta, or gamma and zeta, sorry, is composable. And any possible way I can think of composing them should agree. So gamma with eta zeta should be equal to gamma eta with zeta. I haven't put the dot here for this composite, this multiplication. I'm just using juxtaposition like we usually do in groups or anything. But this is your associativity condition. You just have to put this little caveat at the start to say it's associative when it makes sense. When it doesn't make sense, all bets are off. Second condition is that if like any element is in the groupoid, it must be composable with its inverse. So gamma inverse should always be a composable pair for all gamma in the groupoid. And then, well, it's suggestively called an inverse, so it should act like one. And then we need that for all gamma and eta, which are composable, need that gamma inverse gamma eta should be equal to eta, and that's gamma eta inverse should be equal to gamma. So when you multiply an element by its inverse, you should be undoing that element, which if you're dealing with or if you're looking at a group, that's exactly what you want the group element to do, except you may have noticed that I didn't mention that there exists an identity element. Actually, I should actually say that groupoid should be non-empty. I don't think I've ever actually seen that written down, but we want them to be non-empty because otherwise, well, you can do anything with an empty set. So the kind of part where this really starts to depart from groups is that you have, if gamma and eta are not composable, then like gamma and gamma inverse and eta inverse, or gamma inverse is not equal to eta inverse. And you have all of a sudden have two identities. Why can you have two identities and why can't you do the usual group thing of like slamming one into the other and getting like the same result each time? These aren't composable. They're no longer, this is purely a result of the partial definedness of the multiplication. So we say that, so we start talking about, instead of just an identity, we start talking about our space of identities. We call this G0, and this is called the unit space. And concretely is the set of all gamma inverse for gamma in G. You could also do gamma inverse gamma. You're just swapping you're just putting the inverse in the other place and relabeling. Like the inverse is a bijection, so this changes nothing. We also then get two maps, R and S, from the group to its unit space. R, I'm calling the range map, and R of gamma is going to be this gamma inverse, and S I'm calling the source map, which is going to be gamma inverse gamma. Why have I called them the range and source maps? Well, you can show that a pair is composable precisely when the source of one matches up with the range of the other. So you have the source of gamma equals the range of eta. So if you do a bit of graph theory, think, when do I have an actual path in a graph? It's only when I can match up the head of one arrow to the tail of the next arrow. And in this sense, you read this composition as going from right to left. So this is like the range of eta here should match up with the source of gamma. Reason I go right to left instead of left to right is it matches up with operators when you go into build C-star algebras or representations of these on Hill spaces. So then, what else we got? Okay, a particular class of groupoids that I'm interested in. Should add, if you want to make this a topological groupoid, make all of these things continuous. That's it. Have a topological space, have it. The inverse should be a self-inverse homeomorphism, and the product should be continuous with respect to the subspace of the product topology that you've got in here. Yeah, if you want to make it topological, do everything you would first think to do, and that's it. That's enough. A certain class of topological groupoids which act really, really nicely are what called Atal Groupoids. So G, we say that G is Atal, in the French word for spread. I'm not sure why exactly we call it that. I'm sure someone very smart said, we're calling this Atal, and then a lot of people said yes. But G is Atal if the range and source maps are local homeomorphisms. So what this says is that around every point in your groupoid, you have a kind of a little bit of it, an open neighborhood that looks like the unit space topologically. And you get this by projecting down to the range or projecting down to the source. In fact, you only need one of these to be a local homeomorphism, and the other will be automatically, but I say both just because makes things a bit easier later down the line. But what we get is that this gives you a kind of a discrete light condition on the groupoid. Full discrete on the groupoid would remove any need for topology to begin with, but we want something that acts kind of discretely, but not fully discrete, because when groups are discrete, building group C-star algebras becomes a lot nicer. And so when we build groupoid C-star algebras, we want things to still be nice, but still want to encode topological data. If G is Atal, then what you get, one thing you get is that G subscript X, which you could picture as the source fiber over a point X in the unit space. So if X is in the unit space, the set of points that get mapped to X, the source fiber, is discrete. Precisely because you've taken this, like the source or the pre-image of a point under a local homeomorphism. It's locally a homeomorphism, so none of these points can be close to each other in this fiber. Same with the range, which we call G superscript X. Both of these are discrete, which in particular means you can sum over them and you don't have to worry about integrals. So, and that's what we'll do. And I'll first cover this construction in the Hausdorff setting and then tell you what goes wrong in the non-Hausdorff setting. The answer is a lot very quickly. But if you want to build a group C-star algebra, then you probably want to build a convolution algebra, because it's usually what you do when you want to encode group structure into an algebra, like a group ring or something. So we start with a certain object. We'll say this is the G is Hausdorff case. So G is HD. You start with your first object, which will be the compactly supported functions on your groupoid. So, or continuous functions on your groupoid, taking value in the complex numbers. We want multiplication on this object. So we go, okay, well, if F and G are in compactly supported functions on the groupoid, we'll call this product F star G evaluated at gamma should be the sum of all, like a convolution, you want the sum of all products that become gamma and then take F evaluated one, G evaluated at the other. So you go, okay, well, F of eta times G of eta inverse gamma. But because I'm in a groupoid, I can't just say all eta because my multiplication is only partially defined. So I pick the eta for which this makes sense. Actually, I might, I think it's, yeah. So in this case, the source of eta should match up to the range of gamma. So I'm summing over eta in the source fiber over the range of gamma. Is that possibly too small? I can make that bigger. Yeah, okay. Better? Okay. Perfect. Okay. This gives you an associative multiplication. Great. Please just take my word on that, because I don't want to prove associativity. And as one of my old professors used to say, proof of associativity should be done in the privacy of one's own home. Yeah. Oh yeah, this should be the range. So good pickup. Yeah, this is the range, but so I put an R here. It's just not very visible.
Right, but it's eta inverse has to match up with the range of gamma, right?
Yeah, so eta, the source of eta inverse should. Oh yeah. Okay, I should okay. I'll do it this way. I like dealing with source fibers. I don't know why, but I do. The other thing we need if we want a star algebra is, well, we need a star. So the star is actually pretty easy to define. You just say, okay, well, F star at gamma is going to be F evaluated at gamma inverse, and then take the complex conjugate. This gives you like a star algebra structure on CCG. And so then you ask the question, well, what's stopping it from becoming a C-star algebra? Just need a norm. There are two norms you can get. One's really easy and very non-descriptive. One's a little bit harder to get, but is much more descriptive. First one, you say, okay, take the maximal C star norm on CCG. So first of all, is there a maximal C star norm on CCG? There is. I can't remember the exact proof of why this exists off the top of my head, but it does. And then this gives you the full groupoid C star algebra, which is called C star G. The other option is, like in the group case, we build a regular representation like of the groupoid acting on itself. But because we have a bunch of different units, we have to build a bunch of different representations, one for each unit. Pull up my notes so that I get the formula for this right. So for each unit X in the unit space, we define pi X from CCG to bounded operators on little L2 of the source fiber of X. We can take little L2 because, like I mentioned before, these source and range fibers are all discrete. So little L2 is really the only meaningful thing you can make out of this that looks like a Hilbert space. And you say, okay, well, how is F in CCG going to act? We're going to have pi X of F is going to act on the point mass at gamma by summing over F of alpha and then delta alpha gamma. So each element I multiply by, I am also shifting my point mass around. And then this is, where can these alpha live? Well, clearly the source of alpha has to be the range of gamma because they need to be composable. So we take the alpha in G range of gamma. I've gone too small again, I've just noticed. Delta subscript alpha gamma, alpha in range of gamma. If you think of thinking back to the group case, if you've seen the group construction, this is exactly it. I'm just summing over the entire group and I'm pushing this point mass around to different coordinates. This gives you a representation which will be bounded with, or rather, it will be bounded in the sense of like bounded by the maximal norm. And you can say, okay, well, I can do this for each X in the unit space. And so I can take pi as the direct sum over all of these units. And this is my left regular representation. So then we say, okay, I'll say that the reduced groupoid C star algebra, like you would for a group, is exactly the closure of the image of this under this representation. So you take pi, you apply it to all of CCG, take the closure as a subspace of B of the direct sum of the unit space of little L2 of GX. So this is a very concrete C star algebra. And then you've just taken like a closed subalgebra, star subalgebra of it. So this is the kind of, if you want to actually do computations with the groupoid C star algebra, you would prefer to do this. So once you have this, well, what is this good for is a good question. Like, why would we deal with groupoids in the first place? And one, in my opinion, one very good reason is that they turn out to encompass a huge class of C star algebras. In particular, if you know what a Cartan pair of C star algebras is in the sense of Lenore, then every Cartan pair A inside of B, where A is commutative, so this is C0X, is of the form C0 G0 as a subscript of a slightly more generalized version of this, something called a twisted groupoid C star algebra. Think of having a complex line bundle over your groupoid. and then taking sections of it. This is Lenore, a very significant paper in 2008, said that, okay, every time you have a carton pair, so there is a couple of conditions there, then it looks like one of these. Another paper by Xin Li in 2019, I think, says that every classifiable C-star algebra, so if you know the list of adjectives associated with that, these are separable, simple, nuclear, Z-stable, satisfying the UCT. I missed one. Unital, yeah. Yeah, very important, that one. Okay, well, the result I know, I think, looks at the unital case in particular. Yeah, so like every classifiable C-star algebra has a carton subalgebra. This is a result of Li in, I can't remember the year, but funnily enough, this paper is called Every Simple Classifiable C-star Algebra Has a Carton Subalgebra. So yeah, in particular, these two together tell you that every classifiable C-star algebra is a groupoid C-star algebra, or a twisted groupoid C-star algebra, but still a groupoid C-star algebra. So if you're all interested in the classification program, then there might be some reason to be interested in groupoids, or some reason for interest in groupoids. That's not so much the stuff I work on, though. I am kind of I'm not in the classification sphere, I'm in the groupoid sphere more than anything, but I'm in the groupoid sphere when things get nasty and non-Hausdorff. So now that I've given you like the nice, peaceful, kind of idyllic version of what's going on, it's time to industrialize a little and ask the question, what if G is not Hausdorff? So first things first, I can't just go completely off the rails and say, not like no Hausdorffness at all, I'm going for the indiscrete topology. No, because we would lose all information, lose all notion of any separation of points. So I need to control it a little. So I will insist that we still want that the unit space is locally compact and Hausdorff. So by insisting that the unit space is Hausdorff, oh, and we also want that G is still Atal. If we got rid of Atal, then nothing would be possible ever. But if we have a unit space that is locally compact and Hausdorff, then in particular, we know that the whole groupoid is locally Hausdorff because we have this local homeomorphism from the source or through the source map going down to the unit space. So you always have Hausdorff neighborhoods. Things aren't completely out of control, but it still gets a little wild. And the first thing that happens is that in a non-Hausdorff groupoid, if you take a function on that is compactly supported on an open set, or this happens in just topologic space. If you have a function that is compactly supported on an open set, and then you extend it by 0 to the rest of the space, it may fail to be continuous on the whole space. And the reason for this is because in the non-Hausdorff case, compact no longer implies closed. You can have compact subsets which are not closed. Yeah, it makes everyone uncomfortable, that one. But so what we need to do is instead of just starting with the compactly supported continuous functions on the whole unit space, we want functions that start off as continuous on little areas. So we start looking at instead of looking at this, we start looking at what are called open bisections. So a bisection, definition, a bisection of G is, and I will say open because was that oh, okay, sorry, I thought you had a question. No one. So is an an open subset U of G where S, like the source map and the range map, restrict to injective maps on U. So section, it's a section for both the source and range in that sense, hence bisection. So are injective. Yeah, okay, thanks. And by virtue of being Atal, we can restrict the source and range to local homeomorphisms, which means that we actually have open bisections. And in particular, we can cover our entire groupoid by open bisections. Moreover, since the range and source maps are injective and homeomorphisms on these bisections, the bisections are Hausdorff neighborhoods or Hausdorff subsets, because they're homeomorphic to subsets of the unit space, which we have assumed is Hausdorff. Then we can say, okay, well, I can take a function like CC in CC of U, so something that's continuous and compactly supported on a bisection U, and take something in here, call it F, and we'll map this to something that we suggestively also call F, which is just extending it by 0 to the whole groupoid. So F extended by 0 to a function G to the complex numbers. And we'll call the space of these curly CC of U. These may fail to be continuous on the whole groupoid. That's fine. So some people call these, I think, Ralph Meyer, Bartosz Krasniewski call these quasi-continuous functions on the groupoid. They are the kind of building blocks for what you should be. In the Hausdorff case, these are continuous functions because if you have it compactly supported, its support is then closed, or the closed support is closed in the whole groupoid. So these actually truly do become continuous.
F is defined on O, which is open bisection.
Yeah, F is defined on like U, which is an open bisection, and then we extend by 0.
Right. But on just on U, for example, does it vanish at infinity, for example?
It vanishes on topological infinity for U. That may not be topological infinity for the groupoid. So an example of this might be if you have the line with 2 origins. So if you're familiar with the line with 2 origins, this is the space given by everything to the right of this weird shenanigans here is the standard topology on the interval. And then the neighborhoods of these 2 points are exactly this point here plus the open interval here. The open neighborhoods, like this is locally Hausdorff, because if I just take the neighborhoods that include 1 point but not both, then I get just purely Hausdorff stuff. If I take the function that is just constant 1 on the whole interval and one of the like origins, so I take, by saying that U1 is going to be this most of the interval plus, I'll call this 0 plus. So this top origin will be 0 plus and this bottom origin will be 0 minus. This is an open subset of the space. It's a Hausdorff open subset of the space. And if I take the function that is constant 1 on that, the characteristic on here, 1, this vanishes at topological infinity of this set because this set is closed and compact. Also, no, this set is compact, it's not closed. But if I extend this by 0, so I extend it by 0 to call this chi U1 tilde. And then I say, I'm going to hopefully make this a bit easier to see. If I extend this by 0 to chi tilde U1, then what I get is if I take the sequence of 1 on n, U1 tilde, And well, this converges to, well, this is always equal to 1 for all n, for natural n. But as it approaches, this sequence also approaches O negative as well as O positive. So as 1 on n approaches O minus as well as O plus, we should have that chi u1 tilde should approach both chi u1 of 0 plus, but also chi u1 tilde of O minus. But this is 1 and this is 0. So despite like a function being or having compact support, so in particular vanishing and infinity support on with respect to the infinity of that neighborhood, when you extend it by 0, you may be adding limit points. So this is where the non-closedness but still compact part comes in. Compact is entirely a local property, if you like. You don't need to know anything about the ambient like space that you're embedding to. However, closedness does depend on the ambient space. So that's why this problem exists only when you extend things by 0.
It's yeah, it's a good example, but I mean, I guess in this case, your U1 was already compact, but in general, your U's just have to be open, right? Is that right?
Yeah, in general, the U has to be open, but
and so in that case, you couldn't just take.
I could have just like taken more stuff out here and then made this vanish, like made this function just go. Ooh.
Exactly, yeah, but yeah, it couldn't just be like 1 on some open subset, which is not compact, for example. Then you would,
No.
Yeah,
okay. So that's still not allowed.
Yeah. Okay.
Yeah.
Good.
So what do we do? How do we build a convolution algebra out of this? Well, we need a non-Hausdorff equivalent of these compactly supported functions on the groupoid. So we just say, okay, well, curly C subscript C of G. This is just going to be the span of CCU for all open bisections U. So these functions, I can make sense of this span now because when we have the curly C, we're considering functions from G to the complex numbers that are supported on U, and when you restrict to U, they are continuous. So now, and these are all just functions from G to C, which means I can do this convolution the same way. Nothing changes here because nothing there requires continuity. That's the same, the star as well. So then I can do the same thing. I can build the full, like the maximal groupoid C-star algebra. Cool. I can get C star G, and this is still the maximal completion, or maximal C star completion. It exists by the same reasoning that works for the Hausdorff case. There was nothing there that required the groupoid to be globally Hausdorff, just the unit space in general. You can do a lot with having a nice unit space and then locally everywhere looks like that nice unit space. You can also build the reduced groupoid C-star algebra. And it's the same way. So the same way as the Hausdorff case. Nothing there changes.
If you weren't sufficiently careful and you just decided to do this anyway in the non-Hausdorff case, I mean, so what goes wrong? Do you not get a norm if you?
For the full or reduced or?
Either, I guess.
No, you still get a norm. Everything, like it all works in the sense that you can construct it. What goes wrong is that the reduced, and like this is roughly what I'm going to get to, so the reduced groupoid C-star algebra is no longer, one property it has in the Hausdorff case is that this is the smallest norm that extends the infinity norm on the unit space. So in particular, so this thing here, this is the norm that you have inside of here is the smallest norm that agrees with the sup norm on C0 of G0. So ideally, anything you consider, you should, when you're considering just the unit space, what you're considering essentially are the algebra of continuous functions on the unit space. This is because when you do this convolution product, you've only got one element in the fiber that you can work with in the unit space, and that's the exact element you're evaluating at. So this becomes the pointwise product. This thing always embeds into C, or like C star of G and C star reduced of G. So we want this to be an honest star subalgebra of the full and reduced groupoid C star algebras. So we need a norm that at least is this big. In the Hausdorff case, this is the smallest possible one. I can't remember the exact reasoning behind that, but it is. In the non-Hausdorff case, this fails to be it anymore. You gain too many, the fact that you have extra limit points outside of compact sets, gives you extra representations, which artificially kind of inflates this norm in the non-Hausdorff case. And so I'll give you an example of where this actually genuinely goes wrong. But before I do that, I need a big old diagram that hopefully explains how we build another C star algebra. So then we might say, okay, well, I've mentioned this. Well, if you looked closely at the title of the talk, there's the big phrase at the front that says essential groupoid C star algebras. And I haven't mentioned those yet, so I should probably mention those. So the way we define these, or one way to define these, is by saying, I want to know, I want to have a way of kind of projecting down to this subalgebra that is faithful in a suitable sense. For those of you who do know what this kind of stuff, it's what's called a faithful conditional expectation. And the way you do this in this case is by taking a function and then just restricting it to the unit space. This works on the reduced groupoid C star algebra because you can recognize these as actually functions on the groupoid, honestly. The full one, I don't think this works necessarily, but you can just do it for the reduced one anyway. You want to wait, so you want this way to kind of like project down to the unit space and get something in here. Cool. And you might say, okay, well, what if I do that in the non-Hausdorff case? What if I take something in here and take F in here, and then I just restrict it to the unit space. Like I mentioned, objects in here or objects in here may no longer be continuous. So what you get in here is not necessarily something in C0, G0. Nope. You get something in, you get something that is at least like a Borel measurable with respect to, is just measurable on the unit space and essentially bounded. So because we've just taken something and then we've cut it down to the unit space, and these objects weren't Hausdorff, that's why we can know, well, because these objects may not be continuous, that's why we don't get something that's continuous. We do know, however, that it is measurable because we have a sum of things that are measurable, and when you extend measurable things by 0, they stay measurable in this case, because everything was just, these were open subsets, so we can extend them without worrying about the measures agreeing with things. So then another one, or another thing we do is,
measurable, you mean, you may not have a measure on your G, right? But
I can't remember exactly where we pulled the measure from, but
because you mean measurable with respect to I don't know, what megasets, co-megasets, this kind of thing, right? Like,
yeah, so megasets should go to megasets, and also you can, I can't remember the exact details of which measure we pick, but it is a suitable Borel measure from on the groupoid.
Right.
That it should be compatible with the topology and send megasets to megasets, and yeah. But unfortunately, I don't have more details for you on that just now. But what we might do is, or the way we construct an essential C-star algebra, at least in like a slightly more general setting, is we build a conditional expectation that is slightly generalized, and then we take a quotient that makes this conditional expectation faithful. So what do I mean by conditional expectation? Well, say that E from, so if I've got an inclusion A subset, or as a subalgebra of B, my expectation will be a map from B to, typically, if you're doing a genuine expectation, it will land in A. What we're doing will not land in A, it will land in what's called the local multiplier algebra of A. If you don't know what this is, don't worry. It's an algebra containing A, and it embeds in the injective envelope of A, if you know what that is. But for now, just think of it as something that's bigger than A. So this in particular contains A. And this map should be, or when you apply it to A, because I can clearly apply it to A because A sits inside of B, it should just be the identity on A, and it should be completely positive and contractive and linear. Of course, it should be linear. So this is what sometimes is called a generalized expectation. You can think of it as like a projection down to A. And what we get is, if we want something to, well, we want this to be faithful. And what do I mean by faithful? I say E is faithful. Yep. It's good. Perfect. The only positive element that it sends to 0 is 0 itself. So what it should say is, if I want to detect whether something in for all x in B, if I want to know if an element of B is 0, I should be able to take the positive element that this, well, take this x, multiply it by x star, take the conditional expectation, and I should be able to detect whether it's non-zero. This is the sense of faithfulness. Now I can say, okay, how do I make this conditional expectation faithful? Well, in the right circumstances, asterisk, we can take a quotient of B by an ideal contained in the kernel of here. So I'll call curly n, the subscript E is going to be the largest ideal contained in the kernel of E. And then I'll call B essential this quotient of B by this ideal. Whenever you take this quotient, because this quotient is by something contained in the kernel of E, this conditional expectation will descend down to this essential quotient. And it will always descend to something called almost faithful, which is, as the name might suggest, almost this condition. In nice enough circumstances, which I won't go into the nitty-gritty details of, but in particular these Cartan pairs that I was talking about to satisfy this, you get true faithfulness of this expectation. So then you have something that I'm going to overload the labeling of and call E, and this goes from B essential to M lock A is faithful. I want to do a similar thing for my non-Hausdorff groupoid construction. Is there a particular eraser I should use, the sponge here, or? So if I want to do this to the essential to the non-Hausdorff, like the groupoid C-star algebra for a non-Hausdorff groupoid, I need to know what the local multiply algebra looks like. And luckily, so I need to know what the local multiply algebra of C0 of G0 is. Now, luckily, so first there was a theorem of Gonshaw in the 70s, and then another, I think also Gonshaw again a bit later. So Gonshaw 70s plus. This, for a commutative C-star algebra, this agrees with the injective hull, and in particular, this is the Borel measurable functions with respect to this measure that I didn't specify before, quotient out by meagerly supported functions. Meager, what do I mean by meager? Meager is like in a way of defining like small, like measure zero, but in a purely topological way. So in particular, so if I have a set C where the interior of the closure is empty, then this is meager. And then I just allow myself to take countable unions of these. So countable unions. So meager is exactly countable unions of these objects. Yeah. So for C, a subset of X. I want countable unions because I want to be able to take countable sums in here of functions supported on these things. So you might ask, oh, what does this look like? This is a commutative C-star algebra. What does this look like? What does the spectrum of this look like? That is not a good question to ask. This thing is disgusting. But if you think about like what this does to the interval, all of a sudden you have every measurable function up to meagerness. So you've gone from like continuous functions on the interval to something, so I could take a nice function that goes, it's continuous. I can make it super jagged. I could take like a Weierstrass function. I can have very disgusting but continuous functions. But then when you go to the Borel of mod meager, you can have a function that's on the interval and it just goes all bets are off. But at least we know that we know it looks like this. We know it's much easier to tackle this thing algebraically, in my opinion, than it is to tackle it topologically. This is at least more tangible than trying to figure out what the characters on this thing look like. And so we had before that if I take a function in the reduced groupoid C-star algebra, and I take its restriction to the unit space, I get something in the Borel measurable functions, Borel bounded measurable functions, and then I can just map it again to its equivalence class under this quotient. So G0, and this is in this quotient. So you can think of this as plus meager. And this all of a sudden sits in Borel mod meager of G0, which is exactly the local multiplier algebra of this thing by Gonshaw's theorems. So now I have other thing I should say, this is contractive, positive, linear. It's contractive because you've just restricted a function. It's positive because if you multiply things by their adjoints with the convolution structure that we did before up here, you get something that has at least some support in the unit space. Or if you do something, It's positive because it maps positive things to positive things. I can't remember the exact argument. It's linear because it's clearly linear. What else? Positive, contractive, linear. Yeah, so I've got a conditional expectation. The last thing I need is faithfulness. So I do this essential quotient again. And I say, well, I'm going to take this essential groupoid C star algebra, and I'll define it to be C star reduced of G mod by this ideal we talked about. So I'll call this map going from here to here E of F. Okay, it's not immediately obvious that this taking this quotient does anything. And in the Hausdorff case, you're right, it doesn't. But I'll give you an example where it genuinely does something. So if we take the groupoid G, so example. If we take the groupoid G that consists of a unit space, so I'll call this G0. This thing shouldn't be discrete because discreteness will actually ruin everything. And then at one point, or with one non-trivial fiber. So what I mean by this is I'm going to take a bundle of groups over a space with its like pointwise defined product, except the groups everywhere are going to be 0 except for one fiber. So then I'll let H be a discrete group, non-trivial group. And then say that, okay, the fiber, so G will have trivial fiber everywhere, like so just be this point X for all X in G0, apart from a special one, which I'll call just star. And then G at star, like the fiber at star should just be this group. So then I get H. So what this looks like, I've got a topological blob. Everything's trivial everywhere except at one point, which is this star. I get this discrete group of H. Now, clearly, what's the topology on this? The topology is that it's the normal like topology of whatever you had for G0 everywhere apart from at this group. And then at this group, each point and neighborhood should look like the point and then a neighborhood around here minus the base point. So like a deleted neighborhood of this base point, but then instead, as you're approaching here, you're approaching all of these points in the group. This is fundamentally non-Hausdorff. So if this feels wrong, because it kind of is. But examples kind of like this, or similar enough to this, actually do show up. So then you say, okay, well, what does the full groupoid C star algebra look like? And in a computation, which I am not going to show you, what you get is that the full groupoid C star algebra of G looks like it looks like basically the functions on G0, well, this is a very wavy equals. The functions on G0 apart from this one point, and then at that point, you get a copy of the full group C star algebra for H. And then if I want to say, okay, what about the reduced version? Just stick an R there. And basically, the full and reduced groupoid C star algebras detect this entire group, despite this group existing at a topologically trivial point. If you were to remove this entire group, you are removing a meager subset of the thing. You're removing something that is measure 0, because you've taken, I'll call this countable just to, yeah, doesn't hurt anyone. If I'm going to call that, if this group is going to be discrete, and I'm going to remove countable single points from a topological space, which is very much not discrete, I shouldn't be affecting the measures of things. I shouldn't be affecting the group the group on a huge topological scale, like having a copy of this here. So what you get is, if you look at the essential groupoid C-star algebra, and you think, okay, well, what have I done? I've quotiented out by like meagerly supported things. In particular, I can just remove this point. And so what you get is just the continuous functions on the unit space, truly, which if you're dealing with these non-Hausdorff groupoids and you want to avoid data that just happens at singularities, this is what you want. This is the object you want, because you don't want to accidentally get a copy of the C-star algebra of the free group on n generators just thrown in there. This thing is entirely commutative up to this point. And the general idea, at least in the commutative cases, you want things, if you have something that works on a dense open subset, you want it to work everywhere the same way. And essentiality does this for you. So what did I have next?
It's with the full group C-star algebra.
Yeah, so the full, I just remove this R, remove this R. Yeah. So like with the examples I've seen of this, people put the term, like put amenable in the description of H so that you don't have to worry about anything. And then they say, but if H is not amenable, then you just get the other one.
Yeah, so but even just going back to the reduced one, with that direct sum, you sure it's completely independent? You can have two completely independent things in those.
So when I say these like kind of quotes, what you should actually picture is like this being a bundle over this space, and then you're taking continuous sections. And then the sections at the fiber at this point is like that your sections take are in fact actually C-star of H or C-star reduced of H valued, but only at that point. Everywhere else they're trivial.
Right, but yeah, I know. When you're taking these bisections, I thought that every one of those points in your group is a limit of things that are not in that group, right?
Hmm.
And so when you take a bisection, the value at that point will have to be a limit of things. And
Yes.
then you're,
So the bisections of a point here, the bisection of this point looks like this point plus this deleted neighborhood down here. So you take a function that is like supported along, or it goes up like that, except this bump isn't occurring at this coordinate. It's instead occurring at this coordinate.
Yeah.
So at a non-trivial element. It's kind of hard to draw because three space is Hausdorff. So,
but I think, and of course you can have different bumps, and then you can add them together, right, to get your CC of what the coordinate CC.
Yeah,
right?
yeah. So I can have like a bump here, and then I could have a bump down here, a bit different, and that, or I could have this. I could have the same function, but instead of the neighborhood taking those at this point, I take the neighborhood at the origin, or at this like on the base space. I've added and subtracted the same thing everywhere except at this point where all of a sudden I pick out this value here.
Yeah.
So if I go, and then minus the value here. So like if you look at this kind of 2D and I've got this H going up like this, and then a function that is just, if this is compact, I can just take the compact, like the constant character or the constant one function on the base space. So chi of G0, and then I can take also minus chi of the bisection picking out this point. So this plus here, so I'll call that U. Then if I subtract these, it's one, like both of these agree almost everywhere except at this point, or these 2 points, in which case I get a function which just picks out this point here and this point here.
And then on one bump it'll be 1, on the other bump it'll be -1.
Yep.
Right? So it seems to me like even when you add things together, if you still add up all the bumps on that group, it has to be equal to the limit of the other values not in the group.
Yeah, but you don't add up the limit. You don't add up all of those bumps because each of these is a separate point in the groupoid. You actually get that. Well, you get a function that is on this groupoid just takes a value of 1 here and value of -1 at this point.
Exactly, right? Like,
yeah. So like you could sum over them, but then you're deleting extra information, which is information that we want to delete, but we delete it by saying that this fiber doesn't matter.
Yeah, I mean, I'm not. Yeah, I'm not saying. I'm just saying, like, when you add up all these sections, it seems to me it's not completely arbitrary what the values on the group are, as opposed to what the values outside the group are.
Okay. Yeah. So this particular example, like that is the case, but there are some other non-Hausdorff examples where you have. There's an example I want to cover a bit later if we have time, but this is specific to this groupoid and it can be basically being a group bundle.
Yep.
If you have a groupoid that isn't fully a group bundle, you can actually have some genuine.
Yeah. Okay. Yeah. Just, I mean, it just seems to be the direct sum there is not quite a direct sum. Like it's the value.
Yeah. Yeah. It's not quite a direct sum. This is very much. This is very hand wavy.
Yep. Okay.
Do not trust. It's the vibe. Yeah. Okay, so we've got this essential groupoid C-star algebra, and I've shown you that there is at least one groupoid where it genuinely does differ from the full and reduced. Then okay. You might ask, like the question might come up, okay, when I'm going from this reduced groupoid C-star algebra to the essential groupoid C-star algebra, because I have this quotient map, I can always go this is a quote, like this is a set, this thing exists because this is a quotient of that, so you always have this thing. And then the question might be, what is the kernel of this? Oh gosh, I've gone for an hour. Should I wrap things up? Or?
I mean, usually you have between an hour and a half.
Okay, yeah.
Sometimes lose people online.
Okay. Well, if you've stuck through so far, I'm glad you're here. Thank you for listening to me ramble about why points don't matter. So the question might be, what is the kernel of this map? When do you have something that vanishes in the essential groupoid C-star algebra? And thanks to like a couple of results together from, well, if you piecewise glue a couple of results from Ralph and Bartosz, so you get a corollary of Kwasniewski and Maya. I want to say in 2019, roughly. This kernel, or so this ideal, which I call this kernel of this thing up here, is exactly meagerly or meager supported functions in C star R of G. Now you might say, oh, okay, well, that's obvious because when we took this quotient before up here, we were just quotienting out by meager supported functions anyway. Difference is the quotient, like this kernel, or this ideal that we are quotienting by, this NE, is specifically the functions, or it's the ideal contained in this quotient. Because this quotient, or this kernel, or it's the ideal contained in the kernel of E specifically. E is not a star homomorphism. So E, the kernel of E is not an ideal that you can just quotient by. You have to be careful. It's a subspace, sure, but that's about it. It's closed. Oh, that's nice too. But N sub E is always sits inside here and is almost never the whole thing. For instance, if you have a function that is just supported on a bisection sitting outside of the unit space, you want to know that that function doesn't just die because it didn't intersect the unit space in its support, even though it maybe had huge support outside of the unit space. So what things are contained in here are functions that well, functions eventually that might be, so f is in, it turns out that this is basically all of them, but you have to do a bit of non-trivial stuff to show this, but if f, well, f star f has meager support. So if f is in C star G, if f multiplied by its adjoint has meager support, then f will be in this ideal of what are sometimes called singular elements of the reduced groupoid C-star algebra. So now you know that it multiplied by its adjoint has meager support, and then you eventually deduce using some of the stuff that, some of the machinery that Kwasniewski and Meyer built up, and just like sticky glue, like sticky pasting a couple of results together, and you get that, okay, the things that fall into this, like that die in this quotient are actually meagerly supported functions. So something that is intuitively kind of true actually is true, which is always nice.
So I guess I'm being a bit pedantic, but when you say meagerly supported, I guess you're using this map J, I guess you have from the reduced to actual sections of your.
Yeah. So something I brushed over a bit is that you have what's called the Lenore J-Map, going from the reduced groupoid C-star algebra into, or embedding into the Borel functions on your groupoid. And in fact, Renaud didn't prove that this exists for the non-Hausdorff groupoids. He only proved it for Hausdorff. This is another result of Bartosz and Ralph that shows you that this works in the non-Hausdorff case, and that you have a bunch of, well, you can genuinely think of objects in here as functions on G. So this is non-trivial, but it definitely exists. I just kind of brushed it a bit under because that's not really what this talk was aimed to be about. But you get that this, like, you can think of like, okay, if I go this way and then I just restrict down to the unit space, and then I do a quotient here to the Borel mod meager, this computes with going around to like the conditional expectation way. So, and it makes sense that it does, because if you're thinking of these as functions, if I restrict them and then quotient, or if I quotient then restrict, I should get the same thing, because I haven't messed with the function's values on the unit space until I quotient, but then well, actually even then you kind of only mess with it up to a meager subset, which you then don't care about in the end.
Is it meager only on the unit space, or is it meager on the whole of G, like the J after mapping by J?
This here, yeah, this is on the whole of G.
Yeah, okay.
So, but if it's on the whole of G, then it will be on the meager, on the unit space. The unit space will be open inside of the groupoid by Atal. The Atalness of the groupoid guarantees that the unit space is open. But yeah, these, like, if you have a function that is supported outside of the unit space, with non-meager support, then it will not be mapped to 0. This is genuinely a condition on the whole groupoid. So meager supported like on G. So you don't worry about just its restriction to the unit space. If you multiply it by its adjoint, then you can just worry about the unit space, because if you multiply something by its adjoint, parts of certain bisections will, like a bisection will cancel out with the inverse of that bisection in the multiplication, gave you something in the unit space. So then a question that arose in my research a bit, because I'm kind of halfway between looking at these as essential groupoids in general, and also looking at the Cartan pairs, which I just erased. A question that comes up in like some circumstances is essentially, does if you have this Cartan pair and you have some kind of non-commutative dynamics that occur around it, you build a dual groupoid, you want to know whether this groupoid is like, if I get the same groupoid, if I pick this like a different set of generators for the dynamics. That's my motivation. If it didn't ring true for you, then don't worry. But the question that I do actually have an answer for is I want to say, okay, if I have that H is an open subgroupoid of G, well then, when do they give the same essential groupoid C-star algebra? And when I say equal, I mean that since this is an open subgroupoid, I can take functions in here and extend them by 0 to functions in here, and that induces an inclusion going this way. So it makes sense. When I talk about equality, I mean like considering the essential groupoid C-star algebra of H as a subalgebra of the essential groupoid C-star algebra of G. And to make this consideration, you need open. So otherwise it doesn't work. Then, did you have a question, Karen?
No, I was just trying to.
Okay, am I moving around too much?
No.
Okay. Well, let me know if there's any particular place you want me to stand if it dies completely. So the question, when do these give the same essential groupoid C-star algebra? And you might think, okay, well, since we only care up to meager, and meager things are like sets with empty interior in a way, you might ask, oh, what about, this was my first guess, if H is dense in G? And you might think, okay, yeah, that makes sense. If I have a function that's defined on H, it should like it, or if I have a function on G, it's determined by how it acts on, like, or how it looks on H as a dense thing. Or maybe they're not continuous quite, but maybe if I have enough, yeah. No, this fails. This fails in the Hausdorff case even. So you can consider if your groupoid is just, if G is just the unit interval, considered entirely as just a unit space where you have no multiplication. And then H, if you pick any dense open subset, so for instance, the open interval, then the essential groupoid C-star algebra for G will be the continuous functions on the closed interval. And then for H, you get the functions on the open interval that vanish at 0 and 1. And you get this because if you consider the groupoid C-star algebra of this, I mentioned before that the essential norm should extend the sup norm on the unit space. And I didn't actually prove that it does, but it does. And then you get that this, well, clearly if I take the sup norm on this open set, which is non-compact, I should get a non-unital C-star algebra. This thing is clearly unital. So these two, it doesn't work. Yeah. That's not, no, doesn't work. Okay. And you might say, okay, well, what about if I just take care of the unit space, make things work? Okay, what about if H has the same unit space as G and H is dense? Okay, well, we've certainly dealt with that problem because if I force them to have the same unit space and the whole groupoid is unit space, then they're equal. But you get a little bit, get a slightly more in-depth counterexample, and you have to consider an example of, I think, yeah, it's Excel came up with here's a paper that's just a list of examples of non-Hausdorff groupoids. It's great. But you consider the set Z, which is the interval -1 to 1 cross 0 union 0 cross the interval from -1 to 1 as a subset of R2. So this is like a piece of your axis. Like just this part of R2. And then you take the action on it generated by sigma x is going to be reflect the x-axis, and then sigma y is going to be the linear transformation that reflects the y-axis. And then you get an action of z mod 2 times z mod 2 acting on this space. I should have picked a different letter. So you get an action of this thing acting on this space, and then you can take what's called the germ or the germ groupoid of this by saying my groupoid is going to consist of pairs. So it's going to be a point, or it's going to be a point in Z times one of these elements of the group, or I'll call this omega. So something in my set, something in my group that's acting on my set. Actually, it should be the other way around. And then I want to quotient out by a relation, which I'll say that G, a point T, is equivalent to H at a point, only at a point T. These two have to be equal if G agrees with, or G restricted to some open set agrees with H restricted to some open set for U containing T open. So if I have some neighborhood of this point T in Z, which I'm acting on, where this group element agrees with this group element, then they should be the same. This is a germ relation saying, like, just on a neighborhood. If they agree on a neighborhood, cool. And then, so objects in here look like equivalence classes. The topology you put on this is by saying, basically by saying, my topology should look like G, comma U. Oh. So essentially just pick a group element and then pick a neighborhood of your base space, and you get an open set. This will generate your topology. Then everything's fine away from this like intersection, this origin, because away from this origin, you have everything acting trivially. Well, so you have everything like, sorry, you don't have everything acting trivially. That's a lie. You have that. If I pick a particular group element, say, if I'm at this point here, so this will be the point. Also, this point is -1/2, say, and 0. So that's the coordinate. And then I want to consider the germ of, well, just any group element. So at this coordinate, -1/2, 0. G can do one of two things, essentially. So either, if G can either do nothing, G can reflect the x-axis, which in this case will do something. G can reflect the y-axis, which is nothing at this point, because if I reflect by the y-axis here, I've done nothing. I'm sitting on the x-axis. Or G can do both. But just as I've said, reflecting the y-axis doesn't do anything. I'll pull this down so that the camera can see it. So at this point here, if I reflect, the only thing that matters is whether or not I reflect the x-axis. So the germ group, and what's more, on a neighborhood of this point, all that matters is that I reflect the x-axis. So at this point, I have at -1/2, 0, there exists two germs. So the one generated by sigma x at 1/2, 0, the reflection around x, and the one generated by doing nothing. So the identity and 0. Cool, and you can do this similar thing to actually anywhere other than the origin. So at or anywhere apart from 0, 0. There are two germs. On the vertical axis, it just now depends whether or not you flip vertically. But at 0, there are problems. At 0, you actually get 4 germs. You get that. So at 0, well, the identity, if you pick any neighborhood of 0, it's going to intersect both the vertical axis and the horizontal axis. So at 0, I can consider the germ of the identity at the point 0, 0. And on any neighborhood of the identity, if I act by the identity on a neighborhood of the identity, I have to act by the identity everywhere, because I can pull at here, I can go a little under or over. And that if I know that I act by the identity there because I have the same germ, then I can't have a vertical reflection. Similarly, if I go a little bit to the left or right, I can't have an x-axis reflection, which means that I have to be 0 everywhere, because I can't have this and I can't have this, and these generate the group. If I reflect the x-axis but not the y-axis, then I know that because this agrees, this germ has to, again, because it has to hold on a neighborhood, you know that this reflection only affects the left, right. And if I had a vertical reflection, I would detect it in this neighborhood of 0, 0. So this is not equal to that, which is not equal to reflecting at y for the same reason, which is also not equal to reflecting by both. So sigma x, sigma y. So I get that this transformation groupoid, at every point on away from 0, I have like two kind of germs. I have the germ that does nothing, and I have the germ that reflects that relevant, whichever axis I'm on. When I'm on both axes, I get the germ that does nothing, I get the germ that reflects each of the axes, and I get the germ that also reflects both axes. So I've all of a sudden, if you picture this kind of, I'm going to try and draw 3D and it's going to go terribly. This is your base space, and then above it, you have like the second, you have the, so this base space is the trivial germ. Then you have the non-trivial germ for the x-axis. You have the non-trivial germ for the y-axis. And then you have these 4 points sitting over the center where you have non-trivial x-axis, non-trivial y-axis, and then both of them. This point just exists with no buddies. But whenever you're approaching, like, there should like intuitively be an intersection here between these two, because like, oh yeah, like it looks like they're kind of lining up because this is this sole germ sitting over this y-axis, this is the sole germ sitting over the x-axis, but they don't agree. And in fact, coming up to this point, the germ that reflects the x-axis on the y-axis looks trivial. So you actually have something that's unit space, unit space, unit space, unit space, unit space, jumps up. This is the fundamentally non-Hausdorff part of it. Now I said I was building up a counterexample to something. So what about if I have the unit space and the unit space is equal in this subgroupoid and H is dense? I'm going to remove a point of one of the germs. And if I remove this point here, so if I take G, take out, what's that? That's on the y-axis, and that was the point 0, 1. If I take out this, and I consider just this copy of the interval, I can have a function that is, I can take the characteristic function on this interval, or the function that's just constant 1. Then chi of, what was it? So it would be sigma y, and then the pairing would be the just 0 crossed the interval. This is a function that is 1 everywhere along here. Now, if I'm not allowed to have this point, so if I say h equal to this function has to vanish here. And it has to start vanishing on a neighborhood of that. You have to be able to do this like vanishing at topological infinity of this point because it doesn't exist in the subgroup point. So in particular, I can't pick this. And so no matter what function you pick in H that's supported around that point, there will be a neighborhood of that point for which up to a meager set, it is bounded by epsilon. But you can pick an epsilon and you pick an epsilon less than 1. Yeah. So this condition is also not enough. For essentially the same reason the first one, I just had to build up a more complicated groupoid, which had a bisection that didn't look like the same, well, that looked like the unit space, but wasn't the unit space. The fundamental reason why this doesn't work is that like this point kind of lies on the edge. It lies outside of any bisection in a way. I mean, it always would lie outside a bisection, but it lies outside in a too uncontrolled way. So the answer we actually got to this question was to say, this was proposition. This like these like so if H so G is an open subgroupoid, then oh yeah, G is Atal and unit space is Flickr compact Hausdorff, blah 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 blah. These essential groupoid C-star algebras agree if and only if for every point in the larger groupoid, so in G, there is a neighborhood or there is a bisection that approximates gamma or approximates and like or kind of contains this. But I need to be very specific about what I mean by that. So there is a bisection in H such that gamma lies in the interior of the closure of this bisection. And the source of gamma lies in the source of this bisection. This last bit about the source is why this part fails, because any bisection I take that's close to this point, the source of that bisection will be down here, or down here, or no, actually down here, but will never actually include the endpoint where the source of this point lies. So that's where this comes in. And then we need to take closure. You need to take closure because you need to approximate things, and you need to take interior because you need things to be open. And I think I've annoyed you for long enough, so I will leave it at that. Thank you very much.
Any questions?
Yep.
Just like your setup, then in some cases, at least in the case of your example on the left, it may contain a maximal Hausdorff subgroupoid. In your case, it would be just G0 sitting inside of G.
Yes.
So my question is, if we have such a situation, so we have a non-Hausdorff groupoid and a maximal Hausdorff groupoid inside of it, how to relate is there a way to relate the essential C-star algebra of non-Hausdorff groupoid with the reduced C-star algebra of Hausdorff subgroupoid inside of it? Because again, in your examples, in your examples, they are pretty close, but not identical as far as I can see.
Okay, yeah. Maybe that's certainly the case in this example. I'm just wondering, I haven't thought about this question much. This is a good question. If you do have a maximal Hausdorff subgroupoid, I think you might also need it to be dense. Like might be one thing, because I can't think of a reason why maximal Hausdorff will immediately guarantee that everything is fine. Maybe that does come for free because you have local Hausdorffness, so you can do this kind of gluing together, but it sounds like you kind of have to make a couple of choices and you might not get or there are definitely examples where you don't get this. So like this example with this XL groupoid, you definitely don't get a maximal one. In the case where you do, I don't know. I also don't know. That's a really cool question.
Yeah, just naively, because objection was there on the bottom left corner,
Mm.
kind of indicates that one can consider something like
Yeah, I mean, it's certainly very trivially, if you have this like a Hausdorff subgroupoid that satisfies this, then obviously, and this thing will, but yeah, I don't know. That's cool. Sorry, I can't be a bit more enlightening.
So do people ever talk about the groupoid von Neumann algebra as opposed to the C-star algebra?
Not that I've seen.
It's just that, you know, with the appearance of all these measurable functions, it feels like it might be a.
Yeah, so I like actually, when you take this local multiplier algebra picture, von Neumann algebras are always equal to their own local multiplier algebras. So you wouldn't gain any new, like the difference between the essential and the reduced would be the same. And actually, what that means. So usually you can detect the non-Hausdorffness of the groupoid by looking at the values that this conditional expectation takes when you just restrict to the unit space. If you always get things that lie in the subalgebra, then you have a Hausdorff groupoid in the C-star algebraic case. In the von Neumann algebraic case, you would lose this conditional expectation loses the ability to detect non-Hausdorffness. So I don't know if you would actually gain anything different necessarily.
Yeah, I mean, I guess maybe that was, kind of my point. But I mean, on the flip side, so what? Okay, you mentioned this Cartan pair result in the Hausdorff case.
Yeah,
it's just for classifiable C-star algebras or whatever. But is there something kind of analogous that you're trying to capture with these non-Hausdorff groupoids that makes really the C-star groupoids the right thing to look at?
Yeah, so like one of the things I'm working on in my thesis is to try and take the Cartan picture and change this conditional expectation to take values in the local multiplier algebra. And in doing so, looking at the non-Hausdorff picture underneath. And we've got some pretty positive results saying that we can like classify these in similar ways to what currently exists, similarly to the groupoid classification, also like Excel's classification in terms of Bell bundles and cross products by inverse semigroups, which then is also some stuff with Koźniewski-Meyer. So the goal of that is to, the motivation for this is that we wanted, in particular, to be able to say that these groupoids that we get that generate the dynamics of the system should be, or sorry, like the groupoids generated by looking at the dynamics of the system should be the same if we get the same inclusion. And this is like a stepping stone on the way to proving that. We want to do a non-commutative version, but then everything gets really weird. But I hope that kind of vaguely answers your question. We are like, well, basically changed the conditional expectation to take values in the local multiplier algebra for the Cartan situation. How do the proofs need to change? What other conditions do we need to add? That kind of thing.
Really, going back to your thing, Bisham, where you're asking about von Neumann algebras, I don't know, but it looks to me like it might have something more to do with AW star algebras or monotone closures. Because if you look at like Borel functions on 0, 1, that's a von Neumann algebra. But as soon as you mod out by the meager ideal, I think that turns it into some monotone closed C-star algebra, which is not a von Neumann algebra. Right. So yeah.
You do get AW, like this, that one is an AW star algebra. And in particular, if you have, so it's specifically AW star algebras are equal to their own local multiplier algebras. So since von Neumann algebras are all AW star, then you get the, like that result holds for them. But AW star is a slightly wider class where taking local multipliers doesn't change anything. But in general, I mean, having an AW star, like assuming that you work always with AW star algebras is quite restricting if you want to talk about dynamics on a particular subalgebra. And one of the things we're quite interested in is looking at non-commutative dynamical systems where you are the object you are acting, the space you're acting on is actually a C-star algebra, just a generic one. And in the commutative, or in the classical case, it's a commutative C-star algebra looking like functions on the interval or functions on a nice topological space.
I have one final question. So is there, I don't know, are there good examples of C-star algebras you can get from this sort of essential C-star algebra construction from a non-Hausdorff groupoid that you know can't or would be very difficult to get just from a Hausdorff groupoid?
Ooh. Not off the top of my head, but I might be able to come up with an example for you in sometime in the near future, hopefully. This is something I do actually need to build up a bunch of examples of things of why this is useful. But I think one of the main reasons that we looked at, one of the main motivations that we looked at this local multiplier algebra valued expectation rather than the full one is that whenever you have a C-star dynamical system which looks like an inverse semigroup acting on a C-star algebra, you can always build this local valued expectation. You don't always have a genuine one, but you always have a bidual valued one and a local valued one. And we chose to look at the local valued one because this gave the essential quotient in at least this case and the generalized notion of it.
If an aspect is more possible, is it possible if you had a C-star and the realized groupoid, Hausdorff groupoid, and you had the realized you had a realization of the same C-star, but non-Hausdorff, that you would get a different cartan and you would get
there might be some benefit to the non-Hausdorff.
I don't know exactly. I know that if you have a non-Hausdorff, or if you have the Hausdorff groupoid, then the essential groupoid structure, or the essential groupoid C-star algebra, where did I write it? Somewhere. The essential groupoid C-star algebra agrees with the reduced. So if you have a Hausdorff model for something, it's probably a sane idea to stay with the Hausdorff model. But I think like the main reason we are looking at these non-Hausdorff ones is that there are examples of like, there are a lot of people who want to study just non-Hausdorff groupoids. You have, for instance, Hausdorff groupoids coming from holonomy of foliations that have singularities in them, or the groupoid associated to the Grigorchuk groupoid and its action, or its self-similar action, or a lot of these dynamical systems that have a sudden jump in speed at things.
You're trying to examine the groupoids using C-star algebras as opposed to examining C-star algebras using groupoids.
I'm kind of going both ways. I'm kind of hoping to sandwich and meet in the center. From the C-star algebraic point of view, we want to do a kind of Cartan classification, similar thing, or for like the non-commutative Cartan, like analogous to results of Excel and then Kwasniewski and Meyer. And then from the other side, we want to be able to say, if we have a non-Hausdorff groupoid, what can we tell about the C-star algebraic structure for the people who want to investigate that side? So, and then if we can meet in the middle and then say, okay, like these, like we can kind of get like, okay, this category of objects kind of looks like this category of objects, but or get this kind of like this true isomorphism like Lenore has, where you can say, okay, these pairs are exactly built by these groupoids and these groupoids give exactly these pairs. Something like that would be wonderful. I don't think we'll get the full generality, but we're getting some. We've had to add a few assumptions, but it's looking promising.
Maybe this is more or less actually what you were saying, but it would be interesting if you had, like, say, a non-Hausdorff groupoid model for something that's classifiable, because that might give you some pretty crazy cartans.
Yeah, that could be
interesting.
Yeah, that could be very interesting. So I guess like there is. I don't know exactly what you would gain from immediately from looking at the non-Hausdorff picture, but having a kind of non-Hausdorff geometry, or this kind of idea of a non-commutative geometry, which is what I think of a groupoid as, a non-commutative topological space. You can ask then, if I have a Hausdorff model or something, then a non-Hausdorff model of the same thing, that isn't just me doing this kind of thing where I just add a point or add a group at a point because the essential C-star algebra doesn't see points. Then if I have a genuinely different like looking groupoid model, what does that tell you about the space? And what like kind of, do I then know something? Well, one thing, if you have the same algebraic structure, you can look at invariance of the algebras and then say, okay, what do these translate to in the Hausdorff case and the non-Hausdorff case? And what are these like invariants look like in the topological side of things? So I think, yeah, this is quite interesting actually.
Great. Marzi has a question.
You are interested now in so how algebra is related to the non-Hausdorff groupoid?
Okay, so if you are lucky, and this lucky condition is very like talking about a certain map commuting with suprema between ideals and open subsets of a certain spectrum, you can view most. Well, you can view your cut, like if you have a non-commutative Cartan pair, so A sitting inside of B, where both of these are non-commutative, then you can view A as the, well, you can view, you can get a Fell bundle, F, over, well, like, over your groupoid, G, and then you can take a sectional C-star algebra or a reduced sectional C-star algebra or an essential sectional C-star algebra with a kind of convolution in the same way that we defined before, just incorporating the Fell bundle structure. And what you might get is that A is the sections of this bundle, or the reduced section of this bundle, restricted to the unit space, where this is just a bundle of C-star algebras now. And then B will be the full section, or the sections of the whole bundle. And then your conditional expectation is taking these sections and restricting them to the unit space. This currently exists for a large class of non-commutative Cartan pairs where they have the Hausdorff structure or they have a genuine expectation. In the local expectation case, we should be able to get a similar thing by just changing these with essentials. So, look, well, if it depends on whether the conditional expectation takes values in A or the local multiplier algebra of A, whether you want to do essential or reduced. I mean, if it takes values in A, then they'll agree. So it won't matter there. The essential part only really comes up when you don't have a genuine expectation. Yeah, I think you do need topologically principled there just to ensure that you have this max prime condition on Cartan pairs, or at least you need a condition on the isotropy. Whether it's topologically principled or by virtue of going to the non-Hausdorff case, you might need something stronger. We're still fleshing that out a bit. So.
Okay, any last questions? I don't see any in the audience, so okay. Maybe we can ask questions informally later. But I'd like to thank the speaker again for a very nice talk. And I'd also like to advertise next week's talk. So this will be Edward Bellotta. Hope I pronounced that more or less okay. Who is actually with us now. And he will talk about nowhere scatteredness and the global gloom problem. So hope to see you there.